So my name is Dr. Anna Paltseva. My friends call me Anya, so if you see me under two names, I'm one person. Sometimes people get confused, but it's me. Today's presentation, I will talk about testing soils for heavy metals and developing some remediation techniques based on the expertise that we have in New York City and now down in Louisiana. But before I start, I'll tell you what I do and why I do it. I'm originally from a very small countryside area down in south of Russia, where my parents taught me how to take care of our own land and grow our own vegetables because they are professional agronomists. You can see some pictures from my home, my dog and little watermelons, and cold winters, my niece with her another watermelon. So basically that's the life I grew up with. And I developed a passion and love for growing your own food, for clean ecology, for really beautiful ecosystem, and of course land, non-polluted land. And this background really helped me to value what we have. And I was all excited always to see the pollution, how much people be able to change, like basically scrub our environment. So my personal mission, based on my background, my family trait, is really to educate people about critical importance of our environment, of critical importance of a healthy soil, and also promote healthy produce, vegetables, fruits, berries that are clean from any contaminants, and also have delicious taste and aroma that I grew up with. That's why I put the strawberry here, because it smells amazingly. And in today's presentation, I will tell you about heterogeneity of urban soils, sources of heavy metals, natural and anthropogenic, as well as how we measure heavy metals. We will talk about reference values and go more into plant contamination, touch base on that, and of course tell you how we can fix the problem. And at the end, I was also asked to add some information about containers and how we or which ones to use better to be safe. So here are some of my favorite images of urban soils, and I typically ask I typically make it interactive webinar, but you can write your impression in a text, and I will in the chat, and I will read it later, especially if you're from urban environments and what kind of features you see in your urban environment. But this is New York City soils, and some of them are natural, like the top left corner is actually natural soils from streams of glaciers, from aeolian wind deposits, from lake deposits, and on the right side corner you can see anthropogenic soils. And this is a reality for a lot of urban environments where we have natural soils, of course, but also soils that were affected by humans. And in this case, we had like coal ash deposit, we had dredged material deposits, and of course landfills. A dream profile for any soil scientist is to dig in a landfill profile, because it's fascinating what we can find. Some main features of what urban soils are is actually heterogeneity of the soil. It's a limited soil resource. This is an image of Naples in Italy, and you can see here there are no soil much. It's all covered up by buildings. And the older the city, typically it's more constructed, especially in the inner part, and it really affects the quality of the soil and what we can do with the soil. Of course, it's a limited resource, and also for urban agriculture. And nowadays people come up with all these different green infrastructure ideas and inner gardens. And including in Naples, we went to a garden that was underground. Actually was like an ancient amphitheater that is now under another building, and they had lights, artificial lights in this amphitheater that were producing light. So something interesting. It really highlights how urban soils are unique, how they're limited, and how we can find a ways to work with this type of soil. And of course, also these modified temperatures, as the soil temperature will be different in urban environments due to heat island effect, as not just atmospheric temperatures. And organisms, plants, community will respond in these different temperatures as well. So what are some common urban soil issues? And if you can write in chat, would be interesting for me to learn what urban soil issues you encounter. But here are some highlights I would like to share with you. It's contamination, a lot of pesticides, a lot of petroleum products, heavy metals. Today we'll talk about lead and a little bit of arsenic, asbestos, and many other industrial waste, mining waste, or even legacy contamination from gasoline emissions, from lead paint, from incinerators. They're still present in the soil. The soil compaction is another problem in urban environments because soils are compressed, the composition will change, air packets will change, the water cannot infiltrate through compaction, and it can further lead to other issues with like drainage, of course, lack of life. Further to it can even lead to erosion. And soil sealing is another issue, of course, because we build buildings as covered with asphalt, with concrete, build roads, and it disrupts water cycle, disrupts nutrient cycles. Water cannot go to groundwater to refill underground flows, and organic matter cannot get to the soil to break it down properly, just accumulates on top and sometimes prevents it from water going into the stormwater systems, so it creates even bigger problem. Soil erosion, I mentioned, can come from compaction, from water saturation. If it's water doesn't go through to the groundwater, it can cause the collapse of roads, especially if it's somewhere on the side, if it's topographic features like on it's different elevation, and of course over time it can be due to severe wind or even like natural hurricanes, but if they're frequent, it may affect the infrastructure, and of course, in this case, it's a really severe road erosion. Then we have a climate change. With the climate change, we have longer droughts, we have stronger hurricanes. As I said, it all will affect our soil, and it can redistribute contamination because soils are dry, and they just picks up the particles and distribute it to other potentially not contaminated areas. With water, it can create runoff, or it can cause leaching of something in the topsoil into the groundwater. So it also disrupts the natural pattern and leads to further degradation and erosion. So those are like some common urban issues, but today we'll specifically focus on heavy metals and where they come from. And this will be done in the framework of urban gardening and urban agriculture. I assume some of you urban farmers, not just, but like not only big farmers, but also urban farmers. So you know the benefit of working at least even a small plot, even in a small site in somewhere in the city that gets really beautiful benefits. Food, of course, it's less expensive if you grow your own vegetables than to buy everything in the store. It by working in the soil, in the garden, it gives some health benefits, brings physical activities, reduces stress. It's even known for minimizing criminal activities, and it's a deeper connection to agriculture and nature. So in New York City, for example, there are about 1,500 community gardens. In New Orleans, there are 50. So it's the distribution of gardens is different. It's changing over time, and COVID really showed us how gardens are important for us and what benefits they bring to the community, especially when we have limited access to parks or traveling somewhere. So the small gardens were beneficial to produce food, but also release stress. But like, heavy metals that we commonly found in urban environments are not just coming from anthropogenic sources. We need to know that metals are naturally present in the soil. This is the map to show lead, and next one will be on arsenic. To show that it's a natural distribution of metals, and it may not be the same. Like the patterns can be very different depending on the paired material. So metals come from rocks, come from different minerals, and their natural presence. This is the map just to show the 5 centimeters to top inches of the topsoil. If you Google this USGS metals in soil maps, you will come up with a series of different maps at different horizons. But I want to highlight this, having a certain level of natural elements is normal. But what is not normal is that how much we impact the soil by adding lead, for example, or arsenic through emissions from pesticides or treated wood or any other anthropogenic resources. So to get an idea where natural lead comes from, for example, it comes from galena. It's a common mineral found a lot in the environment. Lead also occurs in the lead sulfate form, in carbonate form, in oxides. You can get it in feldspar minerals, especially if it's a potassium feldspar, and you can find it in micas, in zircon, and magnetite. It doesn't move compared to arsenic, for example, a lot. So it actually stays maybe like in the topsoil. It commonly bonds with other elements like iron and manganese oxides and also hydroxides, and binds well with organic matter and clays. At the end of the presentation, we'll talk with you that it actually sorbs well to organic matter, and that's why we should add compost or mulches to remediate contamination. And then we have arsenic. You can see the distribution of natural arsenic in topsoil as well, the different hotspots. And it's all because, like, I live now in Louisiana, but it's looks like almost so much arsenic, but this arsenic is actually coming, you can see, from the Mississippi rivers, the natural sediment. So the natural background of metals in certain states will be higher than in other states because of the parent material and sediment transportation. So this is really important to keep in mind when you compare the numbers you get in your test results. What is the natural background of your samples? What is the state level of reference values, and where your numbers are? So you need to be a little bit of a scientist in order to see is this really levels are dangerous or not, or it's maybe close to natural environment. So arsenic, properties of arsenic, it's a non-metal, it's a metalloid, and it has affinity for sulfur. Find a lot in arsenic minerals. Can be also found in feldspar and phosphate minerals like apatite, which commonly uses phosphorus fertilizers. In the soil, arsenic can sorb also to iron oxides, hydroxide, clay minerals, and again, organic matter. I included here that in Indiana, soil parent materials are dominantly marine shale, clay teal, a glacier deposit containing a significant amount of shale with arsenic. So some common heavy metal contaminants you find in urban and suburban soils. Here's the list, there are more, but to highlight, arsenic, for example, come from insecticides that we use a lot in horticulture, treated lumber or timber, and cadmium can come from different fertilizers, from sludges, industrial emissions, runoff from the roads. Chromium comes from treated timber or lumber as well, industrial emissions. Copper comes from different fungicides. It can be used for roofing. Mercury, industrial emissions. Nickel, the same thing. Lead, it's lead from gasoline, from lead paint based, or different pesticides. Thallium, coal combustion, and zinc comes from different galvanized materials as well. It can come from cars and distribute into soils next to the road as well. So there are different sources of it. Specifically, I will focus on lead and arsenic. So lead is a neurotoxin and affects cognitive development. Especially, it's important for children. Soil in lead and soil is quite immobile and it doesn't really move. Arsenic is more mobile, it's carcinogen, and it can actually move to the groundwater and potentially contaminate aquifers. The main sources for lead, again, it's lead-based paint, some industrial emissions, and gasoline emissions from legacy contamination, as we like to say, from before it was banned in 1978. So all this lead that was emitted, it's in the soil and can be distributed. And arsenic comes mostly from pesticides and pressure-treated lumber as well. And how we get soil contaminants into human body? It's actually through different pathways: vegetable uptake or plant uptake, something that we eat, through leaching in groundwater runoff. Arsenic is an example of it. It's mobile. But then the main thing is actually going through direct exposure, especially for children that can touch soil, they lick their fingers, they ingest particles. For child to get lead poison is enough to consume a lead paint that is like the tiny piece of a pen, like the part that we write with. That's how much is enough for a kid to get lead poison from like lead paint that can be found in the soil. So ingestion and house dust found to be the most predominant exposure pathways. I don't know how many people are here from Indiana today. Originally, we give this lecture to audience in Purdue University. So for the audience, I included this map to show lead poisoning in children, or exposure rather, of lead in Indiana. And you can see there's some different sites that some of them have higher concentrations, some have lead concentrations. This is a really cool map if you guys want to see where you are in the United States, at least. Reuters, just Google Reuters lead map, and you can scroll around and see what is the exposure for children in the different parts of the country. But even here, you can see there are some hotspots that are very, very dark. So there's some areas a higher lead concentration, some of them lower. And it's still, scientists are trying to fight to prove that soil is one of the pathways for high lead exposure. Very often it's assumed that it's only from lead paint, or it's majority from lead paint. But we should not forget that the lead paint get into the soil, and then from the soil it can be distributed into the house as house dust, or again, kids playing in the playgrounds or in the gardens that has exposed soil and then get ingestion. Here is the map to show New York City distribution of lead in garden soils. We worked, I worked with my PhD advisor, former PhD advisor at Brooklyn College, where we collected over 2,000 samples for this project. And we demonstrate here a very typical pattern of inner city having higher levels of lead or other metals as well, and how they reduce as we get closer to the suburbs. This is very popular to see in other cities. To have this is like New Orleans, again, the inner city where there was a high population, there was more industry, there was like more roads, there's a higher levels of lead, and then it will be distributed closer to suburbs. Here's an interesting study actually done by Howard Milkey in New Orleans. They compared lead data in soil before Katrina and after Katrina, and we see the reduction. They're still not sure what was the main reason for this reduction, because even the areas that were not flooded also so basically there was no difference between areas that were flooded and not flooded. So originally they thought maybe it's the like washed off of runoff, but not really. So they're still figuring out why there was a reduction. But I think the main message here, there's like a reduction over time, and this we really would like to see. Another important piece of information is that soils are very heterogeneous in terms of heavy metals as well. This is just one neighborhood in New York City, Greenpoint and Brooklyn. I don't know if you have anyone from that area right now, but this known industrial site in the past now has been gentrified. And my colleagues at Columbia University, they did the study when they compared backyard samples to public samples from like public parks, streets, and they see there's a way more contamination in the house backyards rather than public areas, because in the public areas, the Department of Parks, the different organizations who do the cleanup, they add mulch, they grow lawn, different plants, they constantly maintain and change something about the soil, while in private backyards, it's typically the owners, and very often they may sell the house, buy a new house, and the new owners don't know what was done before to their land. So the message here is really important for those who have houses, is that you need to know what is the land use history, land use management, and obviously test your soil, especially if you have small children. I had a lot of clients who were testing soil of the potential house before they were buying the house. They wanted to make sure there was no metals, especially lead, present in their backyard because they had little kids. This is not just animated image to show again New Orleans between and different time periods, like before and after the Katrina, like it's quite visual. And this is specifically for blood lead level. So here's an association between soil lead and blood lead levels. There are not many studies who compare soil to blood lead levels at the scale that Tulane professor Dr. Milky did this for more than 30 years of his lifetime dedicated to this study. So it really, you can see this amazing reduction and how they were able to achieve it. And we will learn today at the end of the presentation by covering this contaminated soil with cleaner sediments. This is how we measure soil contamination directly in soil. You can take this gun, it's called X-ray fluorescent analyzer, and you can shoot it directly to the surface, and within 30 seconds, better 90 seconds, we get a result in this screen of like more than 40 elements, including lead, arsenic, cadmium, mercury was present. You can look for bismuth, titanium, and all sorts of things this machine allows to obtain in a matter of a minute. And I just wanted to show what I do now in Lafayette, since I did lots of this research in New York City, but in other cities, collaboration with the scientists from those environments. But in Lafayette, I also started to do this research. Right now, we have like more than 100 samples, but we also start noticing a pattern that downtown will have more lead, and then it will go further. The numbers will drop as we go further from the downtown area that has more roads, that is older part of the city, and the south part, especially that is growing, developed, the cleaning up woods and building houses on top, and that soil is found to be, of course, much cleaner. So these patterns are common for big cities and the smaller urban environments as well. And if we zoom in, not just the city, we look at the city, we look at New York City, we look at New Orleans, we look a little bit in Lafayette, we look in the Greenpoint as a neighborhood, we see heterogeneity in metals. But if you zoom in even further into a vacant lot, this is from Lafayette, Louisiana, we also can see the differences in metal concentrations. And that's why it's important to test not just one representative sample from your entire plot, but actually take several samples and do the screening to obtain results for all these different parts, because you might find where the hot spots are and where you have very natural backgrounds of lead or arsenic or cadmium concentrations. So heterogeneity is something for you to keep in mind, and it's important to test your lot at the different areas. So how we measure heavy metals, I already showed you in the previous video slide. this machine. It's called X-ray fluorescent analyzer, and you can send, I mean, if you're a big farmer, if you work for a company, you can afford to buy an instrument that is between $25,000 to $60,000. In the labs, you can send it to laboratories who do this screening for you, and the prices are much less expensive to pay for the sample that is analyzed with XRF versus mass spectrometers in certified labs, where they get they have to use acids, people's time, and the price become more expensive, and people tend to test less samples. So we believe that it's better to test more with a less accurate equipment, but we'll compensate for this accuracy, lack of accuracy, by doing more samples. And when we compare the data between mass spectrometers and X-ray fluorescent analyzer, we'll see a very high correlation. So it really works to use this equipment, and you can take it in the field, or you send your samples to the lab and they analyze it through the bag. Or maybe they do processing further, which actually increases the accuracy by sieving, by drying samples, sieving it, and crushing, of course, and analyzing through special films that are impurity free, and then you get very good results. And this is a little bit of scientific slide. I want to tell you that what we measure so far, the Shoji measure, those are the total concentrations. And the total means it's all possible forms, chemical forms of a metal that we can measure. But for us, in humans, animals, and plants, it's important to know the bioavailability of the metal. Not everything that we find in the soil can be dangerous for human health, or for animal health, or for plant uptake. It's really the fraction that it can dissolve in the human body or can be uptaken by plants that is most toxic. And to analyze soil for bioavailability is actually very complicated. It's much easier to do it for total concentrations. So to analyze bioavailability, typically it's done on animal studies in vivo in specialized like biological labs, where they feed the soil into an animal, and then they see what percentage is taken up by brain, by kidneys, or goes into blood or urine, which is unethical, time consuming, and of course expensive. Lots of scientists, including myself, we do a lot of experiments to mimic this process in lab conditions. And we call this bioaccessibility, which becomes a proxy to test metal dissolution technically in a gastric solution, which is very close to stomach gastric solution, but we have to make it like mixes of different chemicals with glycine. In my at least lab, we use glycine adjusted to pH of what we find in the gastric system, and do the extraction. So doing this in the lab allows us to do a series of samples, which is less expensive, and we can get a proxy of what percentage of the total concentration of lead, arsenic, cadmium, or whatever metal it can be actually absorbed by human body. And not many labs do this type of analysis, but you have access to any of labs like this. I think Kansas University or Ohio State University used to do this type of tests available to the public. But if you find that some universities are testing for this, that would be really great to do, because this is as close it gets to understand how toxic it's specifically for people. Because when you get results and you find that there's like 1,000 parts per million of lead, of total lead, it may not necessarily say that it's dangerous to people. If it's only 10% bioavailable or bioaccessible, then it's only like 10% of exposure. But if it's 90%, then of course it is very dangerous. So it's really important to know what is the bioavailable or bioaccessible fractions of those total concentrations. But it's much harder to test, and not all labs make it available for people, for gardeners or farmers, and that's why most of labs do total analysis, total concentrations. Knowing all of this, we compared 4 different analytical methods in it was a study done in Canada in a small city, and we analyzed the different methods. I'll just briefly describe that. We used portable X-ray analyzer, this gun that I just showed you. We used the EPA method when we digest the samples with very strong acids like nitric acid, hydrofluoric acid, and hydrochloric acid. Then we had a little bit more mild nitric solution, and there was this solution, like a gastric solution that I showed you in the previous slide, that simulates bioaccessible lead. And you can see here that all these 4 methods actually have really good agreement, which tells us no matter what method you choose, you can have an approximation for another method, and you get a better idea what your soil looks like. So you have a choice what tests are available to you, and there is a way how you can compare the tests among themselves. So once we get this test results, what do they really mean? What we compare them to? I mentioned to you that there are trace elements that are always present in the natural environment, from rocks, from minerals. So it's good to know what's in your area. You can just Google it or see like maybe USGS websites. Sometimes it's a USDA, Department of Agriculture Soil Survey website. They would have data on what is the natural background in your area. So you want to have that number for metals, and then you want to compare it to your state values. There are federal standards for metals and other contaminants, of course, established by EPA, and then there are state reference values or guidelines. Here's an example of just for Indiana, but each state has its own standard line. And we can see that what are the residential requirements, what are the industrial requirements, and they're quite different, and sometimes it's a whole order of magnitude. And just like to compare, like arsenic, for example, is 9.5 in Indiana. In New York, it's 16. Cadmium is 99 here. I think in California it's like 70, and in New York it's 2.5 versus 99. Lead, more or less everywhere in the States, it's about 400. In California is 150. No, in California, it's 80 parts per million or milligram per kilogram. And in Europe, for example, it can vary with 100, 150. So each state or each country has its own thresholds. And there are many different reasons why they were established. So you want to have these references as well. But from empirical observations, studies done by a lot in New Orleans and some other cities, when scientists compare lead data in soil versus blood lead data in children, they find very high association, and the difference starts at about 50 parts per million of lead. Natural levels of lead in environment about like 20 parts per million, depending what part of the country you are in. It's all about parent materials. But when you compare it like in urban environments, it's about when it's 50, after 50, there's an increase in blood lead levels. So something to keep in mind. So you try for at least lead, that is the most serious for kids, for children, is to mitigate it to minimum levels as possible. So definitely more than 400 would be the best. Okay, and here's basically what I just told you. 20 parts per million is the natural occurring backgrounds. The different states have different numbers, 85, like California, Minnesota. Threshold by EPA 400, 600 threshold is for residential areas near Superfund sites, and 1200 for bare soil in non-play areas. So those are concentrations that are established by agencies. Okay, this one I can quickly show you how we use this machine in the field, but it can be used on the surface, and it can be used in the lab just on screening through the bag or special films. And, we just turn the trigger and we can measure it directly on the surface of a soil. Let me get here it is, and just use the trigger directly on the soil, and you can choose the range of seconds you want. For soil, it's better to do like 90 seconds, and then the numbers will come up here. And it's really great resource for not only metals, but if you guys are looking for some nutrients, you want to estimate the total concentration of calcium, of iron or potassium or phosphorus, different metals, this machine can actually show you those numbers as well. So it's not just for metals, but also for different concentrations of elements, from, like, I think from magnesium, I said, to uranium. So it's really great application, and to understand what you can find in the soil. So that's how we measure. And you see that I was doing it in a soil profile, which also suggests that we have differences when we get to different depths. Here's another example from Indiana. They have the study was done like in forested soils, and was close to power plant, relatively close, 5 miles. But we can see the differences in distribution of metals, lead, arsenic, cadmium, selenium in different sites. They really drastically change if we go from topsoil to subsoil, or they may not change that much. But each metal has its own behavior, and sometimes it's very unpredictable. So if you want to know what's in your soil and you have resources to test, it really would be good to see what's in the soil profile and get an idea what potentially can go into the groundwater. And here there was a study done by my student. She also compared the results to the natural rocks in that area, and you can see there was like sandstone. So some sites showed the concentrations that they were higher than the sandstone, and some of them were like below this natural rocks. And for arsenic, they were all higher than what you will find naturally or the residential standard. And you can see that actually residential value guideline was lower than found in the rocks. So now the plant contamination. So we tested for soil metal concentration. We suggest what it might be like if humans consume it, as the bioaccessibility of lead or arsenic or cadmium will be really important to study. But plants can also uptake metals, or they can get contaminated from surrounding areas. It's not necessarily an uptake. Here's the study we did in 2014. We started doing in 2014. There was an article in New York Post talking about community garden that's giving cancer to people. And our group, my lab mates, we went with this machine that you've seen, and we analyzed the topsoil. And we measured through bags, heavy metals, and we found that actually it wasn't true. There was only one area in the community garden that had very high concentrations of arsenic and high levels of lead. The rest of the garden didn't really have arsenic, and there was some sporadic concentrations, like this, like 200 were high for lead. But for the most part, it wasn't really giving cancer to people, as a newspaper suggested. And we also did a lot of analysis of plant and vegetable tissues from this garden and some other sites, like this farm in New Jersey, farm in New Jersey, that has documented the input of lead, arsenic pesticides back in 20th century to fight gypsy moth. So this problem is not only urban and suburban, but also suburban. And in both cases, we planted different vegetables, and we found that regardless the amendment that we applied, you can see my students would also apply different amendments, wanted to see what would be better: phosphorus fertilizers, raised bed topsoil, or compost, or different mixes of phosphorus fertilizers with other like iron and manganese inputs, because we were trying to create pyromorphic, the stable mineral that will combine with lead and phosphorus in the soil. to make it less bioavailable. But what we really found is that plant type is more important than amendment type. And regardless what we added to the soil, the plants had a different response. Herbs and root vegetables had the high concentrations of lead or arsenic in their tissues compared to leafy greens or fruit vegetables. So how does it happen? In herbs or like any maybe even leafy greens, there's like a trap. They trap on the surface of leaves, especially if it's a hairy like parsley, and it's very hard to wash it off, even if you do like triple washing. Carrots uptake lead, for example, through the core inside. So you help to decrease contamination by peeling the carrot, but you can completely get rid of it because it's uptake in. But for radishes, it was different. It's more of adhesion or tension between soil particles and the tissue of a plant, or radish in that case, that would hold on these metals and will not let it be washed away. So you can reduce by washing, but you can't completely wash it off. So something to keep in mind. So peeling really helps when you can peel. The best results were achieved for growing vegetables is actually through growing eggplants, tomatoes, some tall fruity vegetables that don't get enough splashes from surrounding areas, and they have physiological barriers inside that prevents toxicity to go into the plant. Root vegetables or leafy greens do not have such strong physiological barriers inside, and they may let toxins to go through. So plants have different response on contaminants as well. We found that the best amendment was actually compost. It was helpful to add the compost the easy way, but also to dilute concentrations in the soil and also in the plant itself, because yield that we received, like tomato yield, was much higher in composted plots compared to non-composted plots. So there was a double dilution effect. You add compost into the soil and it gives a bigger yield, and bigger biomass has a smaller concentration of metals. And lead, when combined with organic matter, it forms organomineral complexes. It also helps to stabilize it and make it less bioaccessible. So what are the remediation techniques? Nowadays, there are really great emerging organic waste you can use as amendments. You can use coffee grounds and orange and pineapple, banana peels. You can chop them and add them to your garden, add them to your compost. You can see different options here. So organic matter really helps to bind the metals, but also it dilutes the concentrations, and it adds nutrients to the soil. So that really has lots of different benefits that helps to improve the soil quality. There are a couple examples of some programs that exist out there to bring clean soil, and maybe there are something similar in your states or in your countries. New York City Clean Soil Bank, for example, gives away glacier sediments that is excavated when new buildings are about to be built, and the organization gives away the sediment to community organizations for free. But because it's mostly sand, they need to add lots of compost to make it fertile. In Louisiana, there were some studies done when they were using clean sediment from the Mississippi spillway. They tested it, of course, before applying to playgrounds and community gardens in the city as well. So there's a possibility, instead of excavating the contaminated soil, you can bring a new soil and bury contaminated soil underneath. And you can do it with the actual soil or at least compost on top or mulch. Here's the summary of different techniques. There's a paper written on this by my research group. There's a QR code. You can screen it or just Google the name of the article. It's an open access, but you can read a lot more of what I described today, and also read in detail about these techniques. But basically, if we add a compost, if we get mulch, biochar, biosolids, different organic amendments to the soil, it will create a good, healthy environment with good aggregates. It will improve soil structure, reduce erosion, but also help to chelate metals inside of those aggregates. If we add lime, if soil is very like low acidic, we add lime, we increase the soil pH to close to neutral. It helps to make metals less toxic. And you can use different conservation tillage techniques or dust control techniques that keeps dust in where it's supposed to be. It does not distribute the dust and particles and splashes surrounding areas, and the particles, if they have any contaminants in them, will be held on in the ground instead of like being blown away and distributed around the site. And also be aware where you build your gardens or your farms. It should be at least 50 meters from some heavy traffic areas. So the key point from this presentation today is that soils are extremely heterogeneous, and it's really important to study what's in the soil, do different testing. So I highly encourage you to test your soils. Different labs, university labs are great resources for you, but there are different ways how you can mitigate contamination, if it's any. It's changing the chemistry of the soil. You can grow vegetables in contaminated soil. If it's like medium contaminated, like fruit vegetables, you can build raised beds with a field clean material, or at least add compost and mulch. And a couple slides on recommendations for growing crops in container. You need to be aware of what it's made of. Check reviews, read about the manufacturer, and see what material containers are made of. Ask yourself, is the surface porous? Terracotta or unfired clays are porous and can absorb and leach water-soluble chemicals through the surface into the soil. The history of the item. Sometimes people like using, like in this case, you can see from like some machinery. They use tires, and they can also leach chemicals into the soil, or it's a pressure-treated wood that people use. So try to avoid those type of materials. Use mostly plastic that are free from biphenyls A and certain other harmful chemicals. Use a clear plastic bottles, cloudy milk and water jugs, opaque food bottles, food storage bags and squeeze bottles, and some baby bottles or cups and bowls for yogurt, for something that will be better quality. And do not use like soft bottles, commercial cling wraps, polystyrene, styrofoam, plastic wrap, polycarbonates, and so on. Keep plastic containers away from overheating, otherwise there will be release of chemicals, and typically light color containers preferred over black colors, because black color can obviously attract more heat, more absorption of sunlight. And use potting mixes that have a lot of organic matter that can help to and fix chemicals, including lead that we keep talking about today, and create these organomineral complexes in the soil. So if you're curious to test your soil, there are many different labs around the country, but I have one of my own as well. You can send the samples to us. There's a QR code, or just scan it or Google the lab name, and you will see what you can do to send the samples to us. But basically anywhere in the country, you can send to Louisiana, and we can analyze for heavy metals, organic matter, pH, salts, and nutrients and texture in your farm or garden soils, and also amendments. And this is what my lab does. We do lots of engagement with the communities, with the artists, gardeners, give workshops, have a presence on social media. We promote the sustainable practices and some mitigation techniques for soil. And of course, it's an opportunity for student training and a collaboration with other research institutions. So if something piqued your interest through today's presentation, you would like to collaborate or learn more, feel free to reach out. And I'm working on publishing my urban soil guide, and in the near future you might hear from us to share the news video that it's published, and you can learn how to test soils on your own. It will be a fun guide where you can do your own testing and teach your friends, your families, or maybe teach your own classes. Wherever you do, it will be a great resource to follow. Here's my contact information. You're very welcome to email me with any questions you have or potential collaborations. Follow me on Instagram. The QR code is for this too. I have more projects and more videos on my YouTube, just under Anna Paltseva, and also on my website, annapaltseva.com. At this point, I would love to thank you for your attention and ask and get any questions you have. So please feel free to ask me. I'll stop sharing.
Okay, great. Actually, could you put that slide back? Because
sure.
that was a really useful slide with, and I think a lot of listeners might be interested in going to your website and looking at the different resources that you were talking about. So yeah, that was a really interesting presentation, and we're getting a number of questions already. So if you have any other questions, feel free to type them into the Q&A box, and I'll read them aloud as they come in. So just also, I wanted to let you know again that this presentation was recorded, and if there's anything you want to see again, it will be posted on the eOrganic YouTube channel within the coming week. And we have more presentations coming up on urban agriculture and nurturing city soils for healthy organic vegetables. So you're very welcome to go to eorganic.org and go to webinars and sign up for any of those webinars. So getting to the questions, one of the early questions we had was, and this is something that other people have also referred to, a big problem for many is the cost to determine what might be in an urban soil site. The Carl here, who asked that question, tests for lead, mostly in Minneapolis. But what kind of cost would one anticipate to get, sort of a low-end model of one of these XLR machines? What is the cheapest way that somebody could test for soil contaminants?
So it depends what you do. Like if you are a gardener or a small farmer, it's probably cheaper to send it to the lab. And university labs are the cheapest because typically it's non-profit, and we really only pay for operations, or maybe like students, and we're not making profit like commercial labs. Some give an example. So like a lab using the XRF in a lab that I use in my lab, I know Brooklyn College, where I came from, we charge like $10-15 per sample. But from some of my clients, I know it's sometimes the commercial labs charge like $300 a sample. And the difference is that they go to commercial labs and they do product certificates, and because they have to certified, they have to use mass spectrometers. They have to pay for acids, for acid waste, for people time, for processing the data. This builds into the cost for the sample. If you simplify this process, and we use this is the express machine, we call it, it brings the cost down, and that's why it's so inexpensive. And also our purpose is to test more, to provide service to communities. And in return, for us, more interesting is not to make money, is to have the research paper. So it's really the data might be used for research. And that's the main goal for university, at least for a lot of university labs. If it's a big farmer, your consultancy or something else, and you can invest to buy your own XRF because you constantly go to the field, or you have clients you work with, you can buy the cheapest XRF would be, I think, $25,000. The most expensive is $60,000. But you use it for many years ahead, like 10-15 years, it's normal. Or you can rent it from companies, another option. So if you have a site and you so many samples to send to the lab, you don't want to spend that money, you can rent it from a company. And there are so many right now companies who produce them. So you can just go on the website, get in touch with the salespeople, and the typically I had a really great experience with all of them, and see if you can rent it for a week or you can rent it for a month. So it's different options. You can collect samples your own, sample to the lab, send it to the lab. You can buy or rent this equipment, or maybe if you have a university lab that have this equipment, you may have some kind of collaboration with them, and the researchers will come to your garden, your farm, and test it. At least in Brooklyn, we used to do this. A lot of our sites, we had collaboration with community gardens who would ask us to come out, or we had workshops where people would come to the park, like during the farmers market day, and bring their samples to us, and we would test it right there. So another option is to reach out to the researchers who have this instrument, and they can come out to your field and test your samples. Yeah, so it's a really great question, and there are less expensive ways right now to test than used to be. So try to get to the least cost, but more samples, and this XRF is a great way to screen the samples.
Okay, great. That was really helpful. Okay, so here's a question from some of the research that Ellie here has read. Arsenic and cadmium from pressure-treated lumber is not readily leached, and the levels are well below safe levels, both in the soil and vegetables tested, and thus, even if they're present, they're low enough to not pose a significant human health concern. It may also, just as an aside, cause problems with your organic certification. But Ellie also said she's heard that they're somewhat more mobile in acidic soils. Is this accurate?
Yes, yeah. So metals do have a preference for different pHs, and they're least available at a neutral pH or close to neutral pH. But when it's too high or too low, especially when it's too low, there are more metals that will be leached out. Even aluminum that is typically present in earth crust is the most, well, top three. Yeah, it's in the top three most common elements in the earth crust. Aluminum can become toxic if pH is below 4. So pH is really important to maintain indeed. If you tested your product and you know the lead and arsenic or cadmium is not leaching, then it's good. So it's really important to know and investigate what is in your product, and maybe there's some research done related to those products. So if you know it's not leaching, then use it. Just keep testing it over time to make sure it's not leaching. But if you can avoid it, try to avoid it.
Yeah, Ellie also commented that it's great to see how much overlap there is between traditional soil health practices and mitigating exposure to heavy metals.
Absolutely. If you use a compost mulch, it's great for nutrient recycling, for microorganisms. It's great for infiltration, for stopping erosion, and then it's a great resource for mitigation of contaminants for sure. Yeah, there is definitely benefit.
Okay, we've got a question from Dan here. Do you think that fulvic acid is acting as a chelator in the compost?
Fulvic acid from humus, probably. I don't know what is the exact mechanism in the humus, because that's another area of expertise. Something for sure it chelates, something in organic matter chelates heavy metals. I don't know what exactly it what is responsible for it. Yeah, the organic matter and metals, we know it works, but I think people are still looking into what exactly works, what are the mechanisms, and to elaborate more on that. And also we don't know for how long the stabilization will last, like until organic matter breaks down, and then what happened to those metals? Are they going back to the soil or what? So it's really still a really cool ongoing research.
Yeah. Okay, Joelle is asking here, how deep of a soil sample should we take if we're sending them into a lab?
Amazing. That's a great question. So it depends what you're growing. Typically, the topsoil for your vegetable gardens, if it's a lawn, maybe even shallow, if it's a tree or a bush, go to the depths of your tree or bush root. So it's really think what is the root depths of wherever you're planting, and that's the depths you want to take. If it's very deep, you might take topsoil and subsoil. But for the most samples, we typically do topsoil. You just clean a little bit of the surface, and you take not lead containing products. Try to use something, maybe plastic shovel or something that may not leach out potential metals if you're testing for metals, and just take 5 to 6 inches and put it in a bucket or a box. Take in several spots and mix it in. Scoop 1 cup, like half cup of the soil is typically enough, and send it to the lab. And so you create like a representative sample of your area of interest. But if you have different management practices, or you grow different things, you want to, like vegetable garden versus ornamental garden, you may want to take representative sample from each of those locations.
Okay, great. Have you looked at different types of compost for heavy metals? Rebecca here is interested in using harvested aquatic plants for garden compost, but is concerned about possible contamination.
Yeah, we haven't like looked specifically which one better or not, but we did test different compost on the market, and some of the products did have higher metal content than others. I know even some like a community project compost, when we tested them, when the compost was like sitting outside for months, there were some presence of metals. So when you buy products, it's also important to test it. So it's a good investment to buy small bag, test it, and then see what you get, or call a company and see if they tested and they can give you the results. They may not publish it, but they may have it and they're supposed to tell you. But it's a great thing to know and think about when you buy a product, what's in that product. When you create your own compost, you know what you add. But if it comes from somewhere else, even manure can have maybe not lead, but it may have excessive number like zinc or copper or cadmium or something else that commonly gets into the feedstock. So I really need to know what's in the product, and sometimes it's the only way either to call the company and ask, or test the product yourself.
Okay, great. Gerard is asking, what is the efficacy of using a 10% vinegar solution to remove surface particles on leafy vegetables? I assume to clean off the heavy metal.
Yeah, so typical washing helps. We did in the lab triple washing, but it still did not completely wash it off. With vinegar, you again will clean it better. But I know some studies when they were using nitric solution, like nitric acids, like seriously, like acids to wash the vegetables, but they still were not completely able to get rid of some particles that would stuck in like this uneven surfaces on the surface of a leaf or vegetable or something. So it's very, very hard to completely get rid of it if it's stuck in this like little unevenness in the skin. So you definitely reduce it, but it's if it's adhered, it will probably never completely get rid of it. But for us, it's important to remember, if you consume contaminated something, it's not going to kill you right away. It's a consumption over time, right, that will accumulate. And it's important to have different diet, not just eating contaminated carrot, but if you have diverse diet, you're basically diluting it again. So it's not really that dangerous, but you need to be aware what you're eating and where it's coming from.
Okay, great. Sabrina's asking, can you use container gardening to remedy urban soil? And I kind of want to combine that with my own question, and that is, do typical plastic pots that you get for, planting in that are sold at garden centers, are those dangerous or?
That might be the last part of the presentation is related to it. It really, it's what this plastic is made of, what kind of plastic, and what can it leach out. And if it's like overheated in the sun, it may leach some things out of it. If you know it's contaminated, soil container gardener is a solution, and have organic soil in the container. would be a good solution as well. So yes, you can grow container garden and use maybe more organic materials would be better, and also more sustainable. But then this, if you use the plastic, read what the plastic is made of and what can potentially come out of that plastic. Yeah, so the type of plastic matters.
Okay, interesting. Okay, Aaliyah here writes that she has heard of methods of planting sunflowers or fiddle ferns to uptake heavy metals from urban farming sites. The plants are then removed from the sites to reduce concentrations of these metals. Is this an efficient technique, and what is the best way to dispose of the plants that are used for remediation?
Yeah, it's a great question as well. You guys prepared. So the thing about sunflower and lead is a myth. There were some studies done. Well, a colleague of mine wrote a paper actually. I wish I remember the name of it, but it's basically reviewing all possible studies and look what is the efficient plans to remove lead. And we found that there is no plant that actually can uptake enough of lead to remediate it. So it can contaminate the plant, but there is no plant that is hyper accumulator enough to take such high concentrations. It need to be like, it need to uptake it like 1,000 parts per million of lead in its tissue, and none of the plants can do that. The concentration that we got in even our vegetables were like below 1 part per million, and it was enough to be considered harmful for humans. So it's really no plant that is discovered that can uptake that much level of lead. You can contaminate the plant, someone will go in, but it's not enough to clean it up for lead. But for other metals, there are plants, and you can find some phytoremediation databases, and you can find the plant and try to grow it and uptake it. But it will take years as well, and it depends on the climate condition, what type of land, how fast they grow. I know some studies when they grow in Albania in Europe, farmers, instead of growing like farm crop, they started growing weed that was constantly growing in their farms, which drove them crazy. But then they found out through working with researchers that weed actually takes up nickel, and they started to grow that plant to mine the nickel and then sell it to businesses who create nickel crystals and use it for electronics further. So there is such thing as agromining, and when people grow purposely plants to uptake very high concentrations of metals from the soil, but it's not really for lead. It's not efficient to do it for lead. The best way would be to add compost or some different organic method to dilute it rather than trying to grow plants.
Okay,
and
great.
the disposal is still a problem.
Yeah, we've gotten several questions on this topic here. Someone else was wondering about myco, let's see, I guess some sort of myco remediation to uptake metals. So with some type of fungus or mushroom?
Fungi, right, yeah. So I haven't done research on that yet. We are working, well, indeed, you can use mica. I don't know which specific fungi you need to use, but yes, you can do this type of work when you use fungi to mitigate it, and it's supposed to transform lead into pyramorphite, which is a stable mineral, and it's what we want to have. So if you could try that, it might work. And nowadays we're actually doing research collaboration with the University of Buffalo, where we're using dry mycelium to absorb lead into the soil. And maybe in a year from now, I will share with you more details on that, what our results are showing, because right now we are testing preliminary data, and we're testing with some solutions. The next phase would be to test it with actual soil. So there is definitely a lot of potential with fungi, myco remediation, and even dried mycelium. But we need to figure out what are the rates, what are the applications, what are the thickness, and all these wonderful things, and it's not there yet. So hold on that question until sometime next year.
Oh, we'd love to have you back. So I'm going to keep up with it.
Yeah.
Some state agencies, David here is asking, some state agencies are tasked with monitoring buried chemicals such as meth and Superfund sites. These sites aren't always clearly marked, and land records don't always have this information recorded. Have you worked
Mm.
with any state agencies to determine across the state the location of these hazards?
Oh, that's a great question. I know like EPA websites have Superfund sites maps, and it's typically they also have like toxic release sites, or you can work with local governments. Like I know, like in Lafayette, I got to know Lafayette Consolidated Government, and they're really nice guys who can like, yeah, if you need information, we can give you maps, we can tell you where things are. So maybe if you can go to local governments who actually have that in maps in place, you can find from them, but they might not be digitized, and that's why they're not in a like online form. Another really great resource to figure out what it used to be is the sandborne maps. Those maps that sometimes they're not also digitized, and you go on scanned version of it. It's like electronic atlas. You have to like scroll around, but I've used those before to look in New York City sites, and it works. It's tedious, but it works. So you can use sandborne maps to also find what there before and determine if when this brownfield became a brownfield or Superfund site. Yeah, so it's maybe local governments dig into EPA websites more, or sandboard maps.
Okay, yeah, that's really interesting. Here, Julie is asking a question about we have gotten high petrochemical content in commercially made compost and even in homemade compost. How
Mm.
does this interact with heavy metals?
That's a question I don't know, and I would love to know it myself.
Okay, well,
That's an interesting question. I will
yeah,
keep it. I'll keep it in mind, and if I try find something, I will get to you somehow.
sounds
Share
good.
with you.
Okay, yeah, we can contact person if possible. Okay, so here is we have time for one or two more questions here.
Mhm.
This one is one that we've gotten a couple times here. I from John. I appreciated the information on total lead level versus the bioavailability of lead. Can you say more about how a vegetable grower or gardener can practically assess the bioavailability of lead in their garden?
Mm-hmm. Yeah, so for plants, so there's a thing to clarify. Bioavailability can be defined for humans specifically, in bioavailability or phytoavailability, depending who writes an article. It's for plants. And the way to find out what is potentially phyto or plant available is you can send it to the lab. There are some extraction methods labs can do, and I know the Brooklyn College, but I know Cornell for sure doing that, and maybe some other big land grant universities. It's they do extractions for phytoavailable elements, not the total concentration, but specifically for potential plant availability. And it's a different chemicals that they use. So that's why it makes like different extractions. But yeah, you can send it to the lab and tell them it's not for total concentrations, it's for phytoavailable concentrations of nutrients, metals, and test your soil. Or you can send your vegetables to the labs and test themselves. So they will tell you what's in your vegetable. Like I used to test carrots or radishes, tomatoes. For my research, it was presented here. So the labs can do the two. It just less labs will do plant tissues, more labs will do soil tissues. But they're out there, and you can test your vegetables directly. So either vegetables or soil for phytoavailable concentrations.
Okay, here's a really good question from Julie. The compost industry's acceptable levels of contaminants is often higher than the levels that cause human health issues. So it's difficult, and also the state levels vary. So it's difficult to know who to believe and what to do. What suggestions do you have around balancing these diverse standards?
Yes, so try to go for the minimum to right, like to go to the natural levels as much as you can. And I know the pain, it's possible. So if you mix different products that are like a compost, if you do it yourself, then it's you know what to add. So dilution is really solution to pollution. In this case, so if you use a cleaner product, the concentration will be lower. And choose the most stringent concentration level as you can. So among federal, state, or some other guidelines, try to go for the lowest one and compare them to your natural levels that you find. Yeah, so just keep in mind, maybe like for lead, that's like number one you would want to look for, is if it's below 50 parts per million, that would be a good product to use, because that's coming up from the actual research when they compare the blood lead levels with the soil lead levels. And after 50 ppm, there is or milligram per kilogram or something, there is a spike. But below that, kids are not lead poisoned. So that's a good number to aim for.
Okay, there was some interest in the report that you talked about, and all the various reports that you talked about, but I think I know I was interested in looking at the one on the different remediation methods. And so can we find all of those reports on your website at
Yes.
annapaltseva.com?
Yeah, but they're all on the website. You have
Okay.
my articles there, but also this is the QR code for that particular review paper that actually has a lot of this information. So if the one thing you want to read this article with this QR code, because it's the most recent ones, and actually talks about legacy contamination on urban soils, gardens specifically, and it goes into details for more of these techniques and practices. And it has a reference list for other articles you can read about these issues, including phytoremediation and some other techniques. So the reference list in the article is very extensive. It's like more than 100 maybe 150 citations. Also great resource to see who is writing what on this topics around the world.
Okay, yeah, that's really good. So it's legacy lead in urban garden soils, communicating risk and limiting exposure. I think I'll place the link to this article on the eOrganic page that will also have this recording on it, and that way
Yeah,
people
that's a
can
great
find it
idea.
easily. So, and I'll put the link to your website there as well. So I just want to thank you, Anna, for the great presentation, and I'm so glad you could join us and
Thank you for
that it worked.
having me.
Yeah.
Yes.
And thanks to everyone for all the great questions. I know we didn't get to every single question, but you do have the contact information of Anna's website. So hopefully you'll be able to find it. And if there's anything really pressing, please feel free to contact me and I'll do my best to get you an answer. So thanks to everyone today for joining us. And I hope that you can register and join us for the rest of these presentations in the series.
Thank you. I'm definitely interested to attend myself. There's so many amazing talks and researchers. So thank you for organizing all of this. It's really amazing resource, and you make it available for people around the globe, which makes it more appreciated. If you have any questions, guys, feel free to contact me either on social media, Instagram, or emails. I'm happy to talk more and share resources I have. That's what I do. My science is people's science. I like sharing.
Okay. Well, thank you very much.
Thank
Okay,
you.
bye everyone. Okay.
Bye-bye.